Hello there, Mr. Sutton bringing you this lesson on area between curves. In this one, we will be finding the positive area between a set of curves. So in this lesson, we're going to be using integrals to find the positive area between two functions on an interval. But before we do that, agree or disagree, we've been doing this all along. Well, you might be thinking we've never done this before, but actually we kind of have. So up to this point, we've been finding the area between a function and the x-axis. When you take an integral, you're just finding the area under the curve, and that's what we mean by that. However, the x-axis has a special name. That is the line y equals 0. So when you were finding the integral from a to b of f of x dx, you could have thought of this as finding the integral of the distance between f of x and the line y equals 0, or simply f of x minus 0, because we subtract to find the distance between two things. So we're going to upgrade this a little bit because this is kind of limited. This only allows us to work with y equals 0 as our default other function. And it also has the limitation that if f of x is below the x-axis, we're getting negative area out of this. What if we only want positive area, like a total distance kind of situation? So we're going to do two big upgrades today. Our first upgrade is we're going to be able to use any function instead of just y equals 0. So I'm going to call this area between f of g, and I'm going to say that we've got the integral from a to b of f of x minus g of x. So I've simply replaced 0 with g of x, and now if we subtract these two functions, we can find the area between them. Kind of, sort of. What if f is below g? Then we still end up with negative area. So our other upgrade for this is we're going to use absolute value sometimes to avoid negative area. Now, one way to do that is by putting it around the whole integral. You also could put it inside the integral depending on whether or not you're able to use a calculator. Or you could just not include it at all. It turns out you actually don't even need the absolute value if you know that f of x is greater than or equal to g of x on your interval. So we'll take a look at all different cases today. For our first case we'll look at, we're going to use a calculator to find the area between these two curves here and these two vertical lines. A good thing to do right off the bat if you're able to use a calculator, enter your functions as y1 and y2, graph it out and see what you're dealing with. Let me do that now. So here are my y1 and my y2. I just entered f and g in there. And let me just do a zoom 6 to see approximately what these things are doing. So there's a parabola. Here's my exponential function. And before I find the area here, I also have to take into account these vertical lines, which, by the way, you can graph these out if you use second program and option 4. So that's just the draw menu on your calculator. You have to quit out of the graph to really use these vertical lines. And then we do second and then program. And you'll see option 4 is vertical. And then you just put the x value that the vertical line goes through. So we'll do 1 in this case. And let me quit out and just grab that input and do another vertical line at 3. So here's a graph of what we're trying to find. We're trying to find this area right between all of these things here. So to do this, we're going to need an integral, and we're going to need some limits of integration and an integrand. Pause the video and see if you can find both. All right, so for our limits of integration, we're just going to use our vertical lines. So we're going to say area equals integral from 1 to 3. Now for the integrand, we just need to get the distance from top to bottom here. So that's just going to be the g function up here minus the f function. Since we're doing top minus bottom and we know this is always going to come out positive, we don't need absolute value for this. We just need to plug this in the calculator. So I'll use Math 9 to get my integral from 1 to 3, alpha trace to get y2 minus y1, that's g minus f dx, and this comes out to about 17.670. For this next one, we want to find the area enclosed by these curves without a calculator. So I'm going to cheat and show you what this looks like on a graph just to help you visualize. We have a parabola and a line and the small sliver between them at their intersection points. So we can see here, since there's no vertical lines, we're just going to use these intersection points as our limits of integration. And since we don't have a calculator, we're going to have to use a system of equations to find those limits. Pause the video, see if you can find where those x values are. All right, so we have these that both equal y. so they both equal each other, we can write x squared plus 2x equals 3x. Subtract the 3x, factor out an x, and we have x equaling 0 and 1. And now that means we've got the area equaling integral from 0 to 1. But now, do we know which function is on top? I mean, you could try guessing by this picture, but you won't normally have this picture. So if you're not sure which one is the top function, you can use an absolute value outside the integral just to make sure things end up positive. So we have integral from 0 to 1 of what? Well, we want to do one of these functions minus the other. And since the absolute values here, it doesn't matter what order you go in. If you look here in your work, you actually already did this first function minus this second function when you moved everything over to the left side to solve the system. So you can just write x squared minus x, that's really just this stuff minus this stuff, in here. Now we have to integrate it by hand. Pause the video and finish it out if you weren't able to before. So we have absolute value of, this is going to be 1/3 x cubed minus 1/2 x squared from 0 to 1. So that's all this stuff with 1 plugged in minus all this stuff with 0 plugged in. So we've got 1/3 minus 1/2. And then all this 0 stuff just zeroes out and goes away. So 1/3 minus 1/2, that's really 2/6 minus 3/6, negative 1/6, but absolute values there to save the day. So this then ends up being positive 1/6. Now, you wouldn't want to put the absolute value inside the integral if you're doing it by hand, because then you have to integrate an absolute value by hand, and that's a pain. For this last problem, we're going to give you pretty much your worst nightmare for one of these problems, but we'll let you use a calculator. Pause the video, put these in, and see what this looks like on a graph. So there's my y equals. I'm going to zoom 6 this thing because I have no idea what the interval ought to be. There's my sine function, and there's my square root function. And we see that we have a crossing definitely here and here, and at the origin. How about further over there? Not really sure. Let me go to window. And I know I'm not going to have a square root before 0. And let me just make my max x value. We'll make it 15. And we'll zoom fit this thing just to get a really good picture of what's going on. So there's the sine function again. And now my square root function following suit passes harmlessly over the rest of the sine wave. So we really just have these two areas that are bounded by the two functions. So this area and this area. Now, before we go ahead and try to set up an integral, we're not going to be able to do this with just one normal integral. If we're trying to follow the paradigm of top minus bottom, that's great for this first area, but in this next one, the top function from the first set is now the bottom function in the second area. So we're going to have to do some trickery here. Before I do any of that, though, let me actually find these intersection values and store those as constants both on my paper and the calculator so I don't have to keep writing them. So just to let people know what I'm doing, I'm going to say f of x equals g of x, so I'm finding intersection points. And we already know that this happens at x equals 0 at the origin. They clearly run into each other. But now we have these other spots we need the calculator to find. So let me do second trace, option 5, intersect. Let me move my spider closer to the first intersection out of those two that I can't really do without a calculator. Press enter 3 times, and we get about 3.8551. I'm immediately going to quit out of there and store that, the stow button down here, and I'm going to store it as a letter. I'm going to just store it as P. And now let me go back to my graph, alpha trace, intersect again. Let me find that other intersection point, enter 3 times. That gets me about 5.3974. I'm going to quit out again, and I'm going to store this value now as alpha q. There we go, P and Q. So now I have those whenever I need them on the calculator. And I'm actually going to do this on paper too. I'm going to say P equals 3.8 and change. Q equals 5.3974 and change. X equals those things. So now I don't have to keep rewriting them. So I've got my limits of integration possibly. What do I do with them? Well, now we need to set up some integrals. So if you've got multiple areas, one option you could do is to split the integral up. And you have to do this because top minus bottom means different things in different integrals. So we're going to change the integrand when the top and bottom functions change position. So I'll start you off here. We can say area equals the integral from 0 to p, that's this first area here, of g of x minus f of x. That's the square root over the sine function. Don't forget your dx. Pause the video, see if you can get the next integral in this pattern. So for this next one, we need integral from p to q. And now, because the sine is on top, we need to do f of x minus g of x dx. Now for the calculator on this. So here's what I've entered. I've got 0 to p, basically g minus f. And then scrolling over here, we've got p to q, f minus g. All comes out to a grand total of about 11.167. So that's great. And this is actually not a bad method. It's actually the only thing you can do if you don't have a calculator. But this could be kind of nasty if this square root function intersected in more than just these 3 spots. I mean, what if it was a little lower and crossed through like 30 of these sine waves, right? That would be a huge pain. So another way to ensure that we're always adding positive area up, which is what we were doing when we did the change in who is being subtracted from whom, another way to guarantee this is to just use one interval and put an absolute value inside around our integrand. So this would look like the integral from 0 to all the way to q. We're going to do this in one shot, but now I'm going to have the absolute value of, and I guess it doesn't matter, we'll just do f of x minus g of x dx. This ensures that I always end up with positive distances even when the f function is below the g function like in this first area. Let's pause the video and go to the calculator to do this one. So now I'll do math 9 from 0 to alpha q, and then we're doing absolute value. So alpha window, you can pull up absolute value that way. Let me do alpha trace a few times. We need a y1 minus a y2, and we need a dx, and we just need a little time for this to work. And this is going to come out to about, takes a little while here, drum roll, 11.167. Hey, same thing pretty much. So there you have it. So that's it for this one. Hopefully you're not going to need anyone to curve your exam on this. Till next time, Mr. Sutton signing off.